Okay, last time we introduced what an asteroid was. It had to be greater than 100 meters in diameter. Well, now we'll introduce a meteoroid. A meteoroid is smaller fragments of asteroids produced by the breakup of comets. And in general, it's 100 meters or less. So a diameter of 100 meters or less would categorize a meteoroid. These meteoroids are called meteoroids when they're in the void like asteroids. So meteoroids are in the void like asteroids. Meteors are when they burn in the Earth's atmosphere, and meteorites are when they strike Earth's surface. So you have oids in the voids, meteors burn, meteorites strike. Meteor showers. Comets break up and distribute micrometeoroids along the path of the comet, and they kind of remain moving, but they kind of remain in that part of the solar system. So if the Earth's orbit intersects that part of the comet's orbit, then a spectacular meteor shower might occur at the same time every year, because the Earth will go through that part of the comet's orbit at the same time in its revolution around the Sun at the same time every year. These meteor showers are named for the radiant in which they appear to come from. In other words, as you're going through that part of your orbit every year, the shower will occur in a certain part of the sky, and it will appear to be within some constellation in the sky. So the showers are named for that constellation that they are closest to. The Perseids are in August, and the Leonids are in November. These are two of the more famous meteor showers. There's also the Orionids in October, and they're approximately a month apart. You have the Orionids and the Leonids and the Geminids in December, approximately a month apart. In case you don't want to go out early in the morning, usually early in the morning is the best time to go see a meteor shower, because you want to wait until your radiant is high in the sky. If your radiant is low in the sky, you're not going to see very many meteors. So you want to wait until it's high in the sky and darkest sky, and that's early in the morning, like 2 or 3 a.m. is your best bet. So here's a look at a meteor shower in case you don't want to stay up that late. Not real spectacular. You just see one meteor here and there. After a while, it might get spectacular, like a fireworks display. I'm just kidding. Meteorites. If a large meteoroid passes through the Earth's atmosphere, a sufficiently large piece survives and strikes the Earth's surface, producing an explosion and an impact crater. About 100 large impact craters have been discovered on Earth's surface. There were many more at one time, but Earth has a process of disguising these craters through erosion and age. But we can see in the solar system that many of the other objects in the solar system, like the moon and other planets, have definite evidence of being bombarded at one time. Some of the remnant rocks or meteorites have come from our own moon, or even from Mars. So knowing that these meteorites came from Mars, in other words, Mars might have gotten hit by something big at one time, and that splattered off pieces of Mars, and those pieces eventually made their way to Earth and crashed down on Earth. So we have pieces of Mars on Earth, and we can analyze those pieces to see what Mars is like, or at least was like, billions of years ago. And same thing with our moon. We have pieces of the moon on Earth, and one of the more interesting things, since we're headed back to the moon soon as one of NASA's objectives, is to actually find Earth meteorites on the moon. So we'll find pristine pieces of Earth that were thrown off of Earth due to impacts with Earth that made their way to the moon, and those will be pieces of history that, like I said, pristine, so they will be basically untouched history of the Earth from, say, a few billion years ago. So maybe they might have fossils of organisms of life at that time, and that would be really neat. So as we go back to the moon, that would be something very interesting to look at, since we'll be spending more time on the moon, and maybe we can find these meteorites from the Earth. In general, meteorites that we find can be categorized in three major groups. One is a metallic group, consisting mainly of iron and nickel. Another group is a carbonaceous group, consisting mainly of dark organic matter, which is actually the carbon is the key essential ingredient to life as we know it. All life as we know it has carbon in it. Also, meteorites can contain amino acids, which are the building blocks of life. So it's interesting that these components can be transported from place to place through the solar system. We can also have rocky silicate meteorites, which basically are consisting of rock, or silicon dioxide, the major component of rock. These meteorites are as old as the oldest moon rocks, so they are truly pieces, pristine pieces of the early solar nebula. So if you find a meteorite like this, you are looking at a piece of the solar system that is basically the same way it's been since 4.6 billion years ago. So that'd be really neat to find, is to know that here you're looking at something that has been untouched for 4.6 billion years, just basically flying through space with nothing to degrade it for 4.6 billion years. Comets are different from meteoroids and asteroids in that they are mainly consisting of water in the form of ice. So they are basically dirty snowballs of ice and dust. They orbit the Sun in highly elliptical orbits. They're classified as either a short period comet originating from the Kuiper belt, which is just beyond the orbit of Neptune, or a long period comet, which would originate from the Oort cloud, which extends way beyond our solar system out to 50,000 astronomical units, and that is a spherical cloud that sort of surrounds our solar system. Here's a look at the comet structure, the basic comet structure. You have the nucleus of the comet, which is its solid center, consisting of the icy rock or the dirty snowball. You have the coma, which is dust that's been thrown off, and the gas that's being also thrown off from this comet, especially as it's heating up as it gets closer to the Sun. You have a hydrogen envelope, which is invisible to the eye, but could be detected through light techniques or just looking for the element hydrogen. You have a dust tail, which is not indicated well in this diagram, but as material is being thrown off the comet as it approaches the Sun, this material will reflect light, and you'll see this dust up to 1 astronomical unit in length. Also, there's an ion tail. As the comet approaches the Sun will have a solar wind on the comet, and ions will be thrown off of the comet in a radial direction away from the Sun, and so you'll see this ion tail in a radial direction away from the Sun. Discussing the dust tail in more detail. It's composed of dust particles released during the vaporization of the icy matter in the comet in the nucleus. These dust particles reflect sunlight, so it makes the comet much more visible as it gets closer to the sun than it would be when it was approaching the sun. The dust makes it appear broad and diffuse, and again, much more visible. It is slow. It's falling behind the speed of the comet itself, so the dust tail kind of curves behind the comet's path because the comet is moving forward. The dust tail is lagging behind. The ion tail is produced by the emission of ionized atoms and molecules from the comet as the solar wind is hitting the comet. It appears blue in color, points directly away from the sun. So if you were looking at the comet directly and you saw the ion tail, you could follow that direction to where the sun should be. And it'll appear longest and brightest at perihelion. Perihelion meaning, peri meaning the closest approach, helion to the sun. So it's longest and brightest at perihelion, the closest approach of the comet to the sun. Here's a look at a comet coming into the sun. We can see it coming in here. At the top here we have a blue tail, ion tail, and it's not so bright. As it approaches the sun, it starts having matter thrown off, vaporized from the heat of the sun, and we start getting matter thrown off, and the dust tail starts to form, and we start seeing the brighter, more diffuse, broad dust tail as that reflects light, and the ion tail gets larger as well as we reach perihelion right here, and hence the comet on its backside of this orbit is very bright and very much easiest to see. Blue ion tail points directly away from the sun, so as you're looking at the comet you can determine its orientation with the sun. And the dust tail, here's Comet Yucutan. This is not a good example of being close to the sun. It's basically, this picture is just showing the ion tail behind the comet. But here's Comet Kohoutek, and this is a good picture. You got the ion tail going directly straight outward from the comet, so the sun must be down below in this picture, and then you have this broad, diffuse dust tail. So this comet is kind of moving to the right as we're looking at it here, as we see this dust tail lagging behind its motion. Here's a great picture of the comet West, and we can see the ion tail, the blue ion tail here straight out. So the sun is somewhere down over in this direction, and then we see the broad, diffuse dust tail, this bright tail here, which is the reflection of the sun's light off of all those dust particles. As we said, short period comets are within the solar system, are part of our solar system. They originate just beyond Neptune's orbit being around 30 astronomical units away. And they have orbits near the ecliptic plane, maybe plus or minus 20 degrees off of that plane, and they orbit the sun in the same direction as the planet. So evidently their origin is associated with the origin of the solar system. They believe to have originated in the Kuiper Belt, and maybe a gravity of a Jovian planet will pull one of these icy objects inward towards the inner solar system, and then a comet has been born and it will start moving on its way towards the sun. Orbits generally require less than 200 years, so if you have a comet that has a repetition time of less than 200 years, it probably is a short period comet. It probably came from the Kuiper Belt, and it has this orbit near the ecliptic plane. The most famous short period comet is Comet HALLEY. named after Halley, Sir Edmund Halley, sometimes called Halley, Halley's Comet. That's generally the way it's called in the United States, but it's most likely pronounced Halley. A short period comet that orbits the Sun every 76 years. It first was documented to be observed in 240 BC. And it wasn't called Halley back then because he wasn't born yet. But back in 240 BC, they observed this bright object going across the sky and wrote down seeing that. The orbit of Comet Halley is 18 degrees off the ecliptic, and here's a picture of Halley down below here. So the fact that it's so close to the ecliptic is further evidence that it is part of our solar system, part of the originating from the Kuiper Belt. Here's another picture of Comet Halley. Here are some years that it was observed, and in fact Halley himself observed it in 1682, and that's when he started looking back in the record, and he found out that Johannes Kepler had seen the same comet back in 1607, just saw this bright object moving across the sky, and he further looked before that and found that there was documented evidence that this bright object had moved across the sky in 1532. So hence Halley had discovered the periodicity of this comet of about 75 or 76 years and had concluded that it should come again. So he predicted that it would come back in the year 1758, so in 1758 astronomers were looking for Comet Halley, and it didn't appear, at least for most of the year. It finally appeared on December 25th, Christmas Day, 1758. So it did come, but it was, according to the calculations, it was about a year and a half late. And the reason for that was on its previous journey into the solar system, it got slowed down a little bit by the gravity of Jupiter and Saturn. It passed relatively close to them and slowed it down, and hence it took a little bit longer to come back. But Halley was vindicated because it actually did occur when he predicted it to occur. Of course, he didn't know about it because he had died in 1742. In 1986, Halley's comet came by, and at that time there was a number of spacecraft sent to take a look at it, and one of them was the spacecraft Giotto from the European Space Agency, which got pretty close. It got within 600 kilometers of the nucleus, which would be approximately 400 miles from the nucleus of the comet, and snapped this picture of the nucleus of Comet Halley. And we can see some features of the nucleus. We can see the evaporation and dust being thrown off of this comet. But if you heighten this picture and you brighten it a little bit and look at the contrast, you can see in particular what appears to look like an ear here. And you can see a forehead and a nose and maybe a cheekbone here. It really looks to me, I have a vivid imagination evidently, it looks to me like a head. You have the ear, the nose, the forehead, cheekbone. In fact, it looks to me like Sir Halley himself, with the forehead, the nose, and the cheekbone. Maybe that's why they named it Comet Halley. Here's the orbit of Halley. We're looking at Jupiter and Saturn here, and Uranus and Neptune. And Halley's comet goes beyond the orbit of Neptune. It has a highly elliptical orbit, like all comets do. Passes very quickly around the Sun in a matter of months, and then spends the other 76 years way out here. Long period comets. These orbits are not restricted to the ecliptic plane. They may come at any orientation to the plane of the solar system because they're originating from the Oort cloud. The Oort cloud is that spherical cloud way beyond our solar system. So if particles start from there, they could start from anywhere and zip around the sun from any direction. These orbits carry them far beyond Pluto and hence take them a much longer time to complete an orbit. They will require thousands or possibly even millions of years to complete one orbit of the sun. So if you see it once, that's probably it. Here's a look at the Oort cloud, and this little box here is our solar system, and here it is enlarged. So you can see the Kuiper belt and the sun at the center. So that little bit right there is the Kuiper belt, and way beyond that is the Oort cloud, up to 50,000 astronomical units, so 1,000 times further away than the Kuiper belt. Here is an example of a long period comet, Comet Hale-Bopp, discovered in 1995 and came into prominence in 1996 and 1997. Actually was the comet of the century in the 1900s because it was around, it was visible for 18 months. And previous to that, the longest comet that had been recorded to be visible was a comet back in 1811 that had been visible for 9 months. But this was around for 18 months, and it was quite spectacular when it was in the sky. Here's a closer look at Comet Hale-Bopp, discovered by Alan Hale, an amateur astronomer who was looking for comets, and discovered this when it was still quite far away, but it was even bright at that point, at least in terms of comets being that far away. Also discovered simultaneously by another amateur astronomer, Thomas Bopp, who didn't even own a telescope. He was borrowing a telescope from a friend, and they were out in Arizona somewhere, and he saw this this comet. So they both reported it at the same time, and they both got credit for it, so it was named after both of them. What's interesting, another side note to this is this was in the sky for so long that there was a lot of public fanfare over this comet, and there was reports, erroneous reports, that somebody had seen a Saturn-looking object near the tail of this comet, and so it was reported like there was a UFO near the tail of this comet. And unfortunately, there was a cult group called Heaven's Gate that believed that there was a UFO traveling behind this comet, and that they should commit suicide so that they could get onto this flying saucer. So unfortunately, that cult committed suicide. 39 people died. Here's a picture of Comet Hale-Bopp, real beautiful picture. And here is the Andromeda Galaxy, way off here to the left here. That's a bad joke. Sorry. Here's the orientation of Comet Hale-Bopp. Actually, it came in at almost a 90-degree angle, almost perpendicular to the ecliptic plane. So it definitely is evidence that it's from the Oort cloud, as it comes in at 89.4 degrees to the ecliptic plane. Its last approach was calculated to be about 4,000 years ago. There was no record of it at that time. At least we haven't found a record of it at that time. But because it was slowed down again by the planets Jupiter and Saturn, it's predicted that it will come back in about 2,500 years. So it got slowed down, It's got a shorter orbit now. It'll be back in 2,500 years, and I can't wait. On each particular approach of coming into our solar system, it has about a 1 in a billion chance of hitting Earth on any particular approach. So not very likely that it would hit Earth. Of course, it's not very likely that someone would win the lottery either, but not very likely that any of these comets would ever hit Earth. It loses some of its matter by evaporation. So eventually it just may lose all of its matter by evaporation. It could eventually break up, or it could collide with the sun if it passes too close, or with a planet. Most likely, if it's going to collide with a planet, it's going to be one of the big ones, like Jupiter or Saturn. And in fact, there was comet Shoemaker-Levy 9 that collided with Jupiter back in July of 1994. And Shoemaker and Levy were astronomers who had seen this comet pass close to Jupiter, and they made calculations on its orbit, and they realized that the next time it came by, which would be, I think it was like 6 months later, that it was indeed going to collide with the planet. So they knew that it was going to collide, and so they were looking for it when it finally did collide with Jupiter in 1994. And here's a look at Jupiter in the aftermath of this collision. When the comet came into Jupiter, it actually, as it was approaching Jupiter, it started to break up, and broke up into 23 pieces. So all those 23 pieces made their separate collisions with the planet. Here's another look at those collisions with the planet, each of them looking like a multi-nuclear explosion on this huge planet of Jupiter. And what we're looking at is the aftermath of these collisions of these pieces of this comet as it hit Jupiter, because the collisions occurred on the backside of Jupiter. It was just our luck that they hit on the backside, so we had to look at the aftermath of what happened when finally Jupiter rotated to our side. So here, just looking as Jupiter rotates around, we can see the total aftermath of this comet. Alright, I'm just kidding with you. But if you block the jack-o'-lantern face, down below is the aftermath of the collisions of this comet Shoemaker-Levy 9 with the planet Jupiter. And Jupiter is a good planet to have out there because, in a sense, it does take on these comets and these things that are flying in through the solar system. So in a sense, it kind of protects us, kind of cleans out the ecliptic plane for us, and protects us a little bit from us getting hit. Here again is looking at the aftermath of this comet hitting Jupiter. Here's the great red spot on Jupiter, and as we'll talk about in the later chapter, the great red spot of Jupiter is twice the size of Earth. So as we look at these black spots where these pieces of comet hit, they're on the order of the size of Earth. And hence, so we can imagine what this would have done to our own planet. Here's a look on Jupiter. Jupiter is a gaseous planet. It's got some ice levels inside, but it's mainly a gas giant. So after a while, it kind of repairs itself, and we can see after a while the effects of this comet impact is gone. Another way to get rid of comets is for the sun to get rid of them. There are a lot of what we call sun-grazing comets. The solar observatory called SOHO has observed about 400 sun-grazing comets, and if they get too close to the sun, then the sun will evaporate them or destroy them. Looking at these pictures here, the sun is indicated by the white circle here. SOHO tends to block out the sun so it can take pictures of the solar plumes that come out, and you can see these marks, which are these comets approaching it. And oftentimes you see that these solar flares will actually come out and kind of reach for these comets and destroy them as they get close. Once in a while we have objects hitting the Earth, and the aftermath of that might be a crater. Here's one of the more famous craters. It's one of the more beautiful craters, the Bergen crater in Winslow, Arizona. Such a fine sight to see. This crater is approximately 50,000 years old, has a diameter of 1.2 kilometers, so sometimes it's called the mile diameter crater, but it's not quite a mile. Here's another crater in Wolfe Creek, Australia. You can see part of the remnant of that impact in the middle. This one is 300,000 years old. Here's Botswana, Ghana, Africa. 1.3 million years old, diameter 8.5 kilometers. Here's Gosses Bluff in Australia. Not much around it. 143 million years old, 24 kilometers in diameter. Here's Arunga in Sahara Desert, Africa. This is underneath all the sand of the desert, so you have to use radar in order to see this crater. 200 million years old, 17 kilometers in diameter. Here's the Manicouagan Reservoir in Quebec, Canada, and definite crater. You can see that the rim is filled up with water. 212 million years ago, 100 kilometers in diameter. Curiously enough, there was a large extinction about 212 million years ago. Here, another look at the Manicouagan Reservoir in Quebec, Canada. Here's Clearwater Lakes in Quebec, Canada. Actually, two craters. What are the odds that two asteroid or meteoroids hit near the same spot? Well, actually, what happened was probably a similar thing to what happened to Jupiter. This asteroid was coming in, and it broke up on its approach and made two craters near each other. 290 million years old. The most famous, though, is the Yucutan impact about 65 million years ago. So we look at here, here's Florida over here. Here we are in northern Alabama. And so we're not too far from where this hit the Earth. Yucatan Peninsula is down here in Mexico at this tip on the Gulf of Mexico. The general accepted theory now is that this impact with the Yucatan Peninsula was the event that killed the dinosaurs. If you were a geologist, you could go back all the way around anywhere in the world, and as you were looking through layers of time and the geology of the world, you would find a layer that is 65 million years old, where there's a lot of iridium in that layer, way beyond normal amounts. Iridium is a rare element on the Earth, but it's common in asteroids. So as this asteroid hit, it left this residue of iridium all around the Earth, and you find it everywhere around the Earth at the boundary of 65 million years ago, which is when the dinosaurs went extinct. So here are some pterodactyls observing this asteroid coming in and hitting the Earth. Actual picture, actually. as a big impact of this would hit the Earth, it would basically melt all the rock around it, and you might see something like this water droplet, where you actually would see a double crater. You see the original crater, it hits, the middle kind of jumps up, and then as it resettles, you have something that looks like this double crater here. We saw the effects of that with that Manicouagan reservoir, where the water actually settled in the outer rim here, but it's really a double crater with material higher in the middle here. Well, here's a picture of the Yucutan Peninsula, the impact of 65 million years ago at Chicxulub in Mexico. And this is a radar picture again, because there is about a kilometer of limestone above this crater. So there's been a lot of ocean activity over the 65 million years, have deposited all this limestone here. 180 kilometers in diameter. Here's a look at that rim of that crater. This is the Chicxulub crater on the Yucatan Peninsula. Swampland and 1 kilometer of limestone above it. Probably was a 10-mile asteroid or comet. The rim is about 150 miles in diameter. And most scientists would agree that this caused the extinction of the dinosaurs. There's other theories for the extinction of the dinosaurs. There was increased volcanic activity at that time. Maybe it's a combination of both that resulted in the extinction of the dinosaurs. There's another large crater on the Earth, the Wilkes Land crater impact event, and it hit the Gondwana supercontinent. Here's the Gondwana supercontinent, just the southern portion of what would have been the supercontinent of Pangaea. And here we see what in the future would have been Africa, South America, Antarctica, and Australia. And the impact here was just below Australia in Antarctica. And right after the timing of this impact, there was the breakup of this Gondwana supercontinent. Here's another look at the impact point here on Antarctica, looking at the crustal thickness of that continent. Here's another way to look at it through gravity fluctuations and radar. This land crater is 300 miles in diameter and about 3 times the diameter of Chicxulub, so it was a bigger impact. You have to use radar and gravity fluctuations because it's underneath a lot of ice. This could date back to about 250 million years, which would be also near the date of a very large extinction, the largest extinction on record, the Permian-Triassic extinction, where 90% of the species on Earth, of all species on Earth, died out. Here's a crater comparison in the solar system. The craters we've just noted that hit Earth are big craters on Earth, but they are small compared to some of the other craters in the solar system. Here's the Chicxulub Yucatan Peninsula crater. Here's the Wilkes Land crater that we just talked about in Antarctica. Here's the Mare Imbrium on the Moon, a very large crater on the Moon, and a lot of the mountains on the Moon are the result of these crater impacts that push the material out to the rim and create these mountains. Here's the Chloris Basin on Mercury, a very large crater taking up a very large piece of Mercury. Here's a crater on Valhalla, Callisto, which is one of the Galilean moons around Jupiter. Callisto is a big, icy, dirty ice ball and hence when this object hit Callisto, it basically melted the ice ball, and before anything else could form, the water starts to freeze back. So you have all these ripples that have been frozen in from this impact crater event. We'll see more of this when we look at those moons of Jupiter in a future chapter. And here's a real large impact on Mars, the Hellas Basin. Incredible impact on Mars. Mars, unfortunately, is near the asteroid belt, so it's probably been pelted many times by asteroids in the past. In fact, 2 of its moons, the 2 moons it has, are captured asteroids. And so if Mars ever did have life on it, it probably was extinguished easily by these impacts of asteroids on the planet. Here again is the frequency of large impacts on the Earth. We expect a couple every million years or so. We had a large impact back in 1908 in Siberia, the Tunguska impact, and it had the effect of several nuclear bombs, much more than a megaton of TNT energy. Here's the explosion that was recorded on camera in Spain in November of 2003. And here's what maybe the Tunguska impact might have looked like back in 1908 in Siberia. Again, another artist's conception of it was through science has been determined that it didn't actually impact the Earth. It actually came in and exploded before the major part of the asteroid or comet actually impacted the Earth. The result was devastation for many miles in the area of Siberia. No survivors known, but there wasn't much known to be what occurred there in Siberia, because it's a very remote area of the world, and so there were not too many people who lived there. Here's tree damage due to the Tunguska explosion. This explosion occurred in 1908. These pictures weren't taken until almost 20 years later, in 1927, and we still see that the trees are down. And in fact, here's a picture taken 90 years later, in 1998, and we can still see the damage from this explosion in 1908, the Tunguska impact. Here's another picture from 1927 showing all these trees, this forest of trees, flattened to the ground. Here's 1927, 13 miles away from the epicenter of this explosion. Here's a picture 30 years after the explosion. Still, this is the first aerial shot. Someone actually finally flew over the area, and you can see that the trees are just still down. Here's the epicenter in 1927, and you can see some of the trees are directly upright. So just like what was observed after nuclear explosions, where the matter is sent straight downward, and things that are upright just below your epicenter remain upright because there's no pressure on either side to force it down. It just remains upright. So some of these trees are exactly upright at the epicenter. Here's the epicenter in 1990. Here's tree damage 13 miles out in 1990. Still evidence of the Tunguska explosion in 1908. Here's 40 miles away in 1990. So we don't want these things hitting us, and that's one objective of astronomers is to find possibilities of these objects coming toward us so that we can do something about them. And probably one of the best things to do is to try to send a nuclear device, explode it near one of these objects to deflect it so it doesn't hit Earth. You could try to annihilate the object as it's coming in, but that might just make it go out in more pieces, and those pieces could hit us as well. And we saw what happened to Jupiter. I mean, each piece was like a nuclear explosion. So maybe that may not work as we, and hence hopefully that might deflect it off course. That's one of the theories. Or you could construct a solar sail and use the solar wind to kind of pull the asteroid off course. One of the astronauts has even suggested that if you just flew near it, you could use the gravity of the spacecraft to kind of pull it off course, but that doesn't make sense to me. Gravity would just be way too weak. Best thing I think would be to deflect it using a nuclear explosion. Here are some other observations of meteoroids, actually micrometeoroids and interplanetary dust. There are two celestial phenomena that are due to light reflected off the dust in the ecliptic plane. You know, the ecliptic plane is where all this solar system development occurred, and also left in that plane is dust. So at certain times when the sun hits that dust, we can see this light in the sky. It's most easily seen when the ecliptic plane is vertical to the horizon. In other words, it's perpendicular to the horizon. This occurs near the equinoxes in either the spring and September, in spring and March, and the fall in September. We call this light that reflects off this dust that's nearest the sun after it has set the zodiacal light. It's a faint band of light that is along the zodiac or the ecliptic plane, and you would see it right around twilight, right nearest the sun as soon as the sun is set, so that the sun itself is blocked from view. Exactly opposite the sun, also in the ecliptic plane, you might see a counterglow, which is called Gegenschein. Again, it's just the dust reflecting light from the sun back towards you. It's relatively faint, but you could see this in relation to the rest of the sky, diametrically opposed to the sun. Here's a picture of zodiacal light. And you can see it extending up from the horizon in a vertical direction near twilight. Here's another. It's a little bit more obvious in this picture. Sun has just set, and you can see this light extending upward, directly up from the horizon. Here's a picture of Gegenschein, or opposition light. Looking in the opposite part of the sky, we see a bright area, which is the dust from the ecliptic plane, and it's just being shown from the backside from the sun, and then we see that light reflected back to us. Another picture of Gegenschein. That concludes this discussion of our solar system, the general aspects of our solar system in Chapter 4.